Okay, so we're going to talk a little bit about Hadoop, big data, and analytics for that data. So I wanted to start off with just a couple brief slides on Hadoop. Most of you probably already know what it is, but we'll cover it anyway. All right, so Hadoop lets you run applications to analyze data, and it runs it on commodity hardware. It implements the MapReduce algorithm, and we'll go to the paradigm, and it supports a highly redundant file system, a database, and a SQL storage access method. So unstructured data is mapped into key value pairs by MapReduce. So if you're selling an 18-foot red canoe or selling an 18-foot red sailboat, how does somebody find that you're doing that? What MapReduce does is map those into key value pairs and then allows a quick search function to look up the keywords and identify which articles contain those pairings. And that's the nuts and bolts of simply what Hadoop does. Now, traditionally, Hadoop has had some interesting heuristics about how you build out a Hadoop server. And the paradigm is that you bring the computation to the data. You use one large, typically cheap SATA drive per CPU core in your server, and you have triple redundancy that's implemented over a 1 gig network. And typically, you've only had a single name node that allows you to look up where the data is located. So some of the problems with that: computational nodes run hot. So they run into a small problem with disk drives and data computation at the same time. The disk drives block the airflow. The core count is increasing on servers. We're now up to 24 cores on typical dual socket servers, and getting 24 drives into a 1U chassis just doesn't make it. And the disk drives are very large, so the redundant recovery takes a long time, like 3.5 hours just for a terabyte of data. So high availability needs some work. The name node and job tracker have been single points of failure. Now, there's been work done recently to make a redundant name node, but that's still not quite ready for prime time. It's just getting into the market today. It hasn't had a lot of shakedown time. And data nodes with bad disks or corrupted file systems, they can take down your entire cluster. So it takes a long time to repair these systems. And they can take weeks to deploy. So you're also missing some critical features at an enterprise level. Doing snapshots, deduplication, copy on write, which we'll talk about in a few moments, and you can't leverage SSDs to use a true hierarchical file system that speeds up access to data. And there's no way to compress your metadata to save on the storage for that. We have worked with a number of large internet properties to develop a whole new paradigm around how you do Hadoop. Basically, you separate the Hadoop operation into a compute node, link it via 10 gig Ethernet NICs to a back-end data store so that you can keep your storage as a separate process. And we'll talk about why this works extremely well. We've built in a Hadoop plugin so that you plug into Hadoop a small module that exposes the HDFS file system that's built on top of Nexenta Store. Now with this, you get the advantage of being able to run the name node as a high availability server using standard techniques with our standard HA servers. Then you have all of your data nodes, and they provide the Hadoop clients that provide the various utilities that you use for Hadoop. The Hadoop plugin basically makes Hadoop think that Nexenta Store is just another file system, an HDFS. It doesn't know that something magical is happening in the background. And you get a lot of advantages by doing this. So you get automatic disk recovery with hot sparing of disks. Data corruption and data detection is automatically healed. The Cloudera manager doesn't even know that it doesn't have raw disks. It has a full Nexenta store visibility, so that you can even add or replace disk operations or even do thin provisioning in a Hadoop environment. So we provide high availability and NFS version 4 services for the name node, and we can replace nodes very quickly. One of the other pieces is being able to do snapshots and rollbacks. We can snapshot the data live on Nexenta Store and then do a backup of that data to a separate data store as a background process on your data node server. And we can then do full backup, full replication, inline dedupe of all of your Hadoop data. You can't do that in a Hadoop system today. The checksum algorithm is a cryptographic hashing algorithm that gives you high data integrity so that you guarantee that you don't suffer from bit rot. And we leverage the SSDs for read-write caches, as Chris mentioned, using the STEC solid-state RAM drives is one of the best and most efficient ways to speed up writing data. This slide is a little hard to read, but it illustrates that you've got 3 different paradigms here. The one on the bottom left is the Hadoop Cloud Manager, and that gives you a view of the data just from a Hadoop perspective. The fact that Nexenta stores underneath is invisible to a Hadoop user. On the top right, you have the Nexenta console, which you can see over at the Data On booth. We've got some cooperation with them on showing off some of this capability. And then you can even take it down to a command line level so that you can write scripts that manage your data for you in the background. So why use Nexenta Store? It's because of ZFS. ZFS provides a copy on write capability. Once you lay down data, you never modify it. You never do a read, modify, write cycle with the ZFS file system. So that you've never overwritten data, you always make a new copy of the data. So that you don't have to do FSCK, you don't have to rebuild, you don't have corrupted files laying around. And it's very easy to recover if there is data corruption from human error, because you can always back up to a previous version of any file in the system. And then scrub is one of the tasks that runs in the background to guarantee data integrity and rebuild your files as needed. We provide the checksumming that's far superior to the checksumming that's provided by any hardware drive or RAID system today. So we can automatically detect and correct errors on the fly using either mirrored copies of data or RAID copies of data. We have a special form of RAID that allows you to recover your data. So let's take a look at how we lay down data. Here we've laid down the initial blocks of a file, and we call it transaction group 19. Then we put in the metadata. The metadata blocks hold the checksums, the cryptographic checksums that protect the data. Every time we read a block of data, we compare a computed checksum against the checksum that's in the metadata block, so that you never, ever get presented with corrupted data. And then when you're ready to finish that file update, you hang the file onto the file system. That's an atomic operation. Everything up to this point has been a lazy asynchronous operation. The top level dnode write is a synchronous atomic operation, so that either the file's not there or it's there in one single step. So then let's say we want to snapshot it. Well, all we have to do is tag the metadata. We don't have to visit every data block in the file system. And when we tag the metadata, all we say is don't delete what the metadata points to. So now once you've taken that snapshot, you can back up your data at leisure. Because if someone comes along and modifies the data on the fly, then what you can do is copy on write. The original data is untouched. The new data is placed in an entirely separate block, and then a new tree is built up to point to the new data plus the old data. And this is where you get a very inexpensive and cheap deduplication of your files as well. So let's
take the third snapshot, or second snapshot, and then make a third update to the file, and we build in a new metadata, hang that onto the file system, and you say, oops, that was human error. You didn't want that update. So you want to roll that back. All you have to do is delete those blocks, and it frees them up from the file system. All done as atomic operations. None of your data is corrupted.
So by decoupling the storage from the compute, we can add disks to the data pool dynamically on the fly without shutting down the system. You can plug in hot pluggable drives to add to the capacity. You can store very large files by spanning striped drives that far exceed anything you can do with ext3 or ext4 or even HDFS file systems. We provide the software RAID. It fixes the RAID 5 write hole. When you're using RAID 5, even with hardware controllers, every time you update in that RAID array, you update on one disk stripe, you then have to read out the other 3 or 4 disks that make up that RAID array, recompute a new checksum, and write a second disk for the checksum. In that set of operations, there's a high probability that you can have a failure that can silently corrupt your data. Whereas with ZFS, everything is done in one atomic operation. The file's there, or it's not there, and then it's there. No intermediate steps that can get corrupted. So we can also simplify your storage management by improving the maintenance and the replication. We can save up to 50% on your networking traffic by doing replications locally across the SAS bus rather than having to go across the network. So we get compression, deduplication, snapshots, variable block sizes, and that leads to all these benefits at an enterprise level. I'm not going to belabor it since you can read the slides and they'll be available from us whenever you want them. And that is all I've got to cover, I think. Or did I leave something out? There I did. Sorry, I forgot the SSD. The SSD gives you the caching. When you read data, it moves it up from the hard disk drive to the solid state drive automatically and keeps it there only for as long as it's needed, and then it's just flushed from that solid state drive. So we can provide consistent snapshotting, a variety of compression algorithms, deduplication to minimize your storage capacity and speed up your local read operations with caching and your write operations with the ZIL using the STEC RAM drive. So it gives you the best of both worlds to combine Nexenta Store with Hadoop. You get safe, reliable, and redundant storage. You integrate with your existing storage infrastructure. So now in your Nexenta Store, you can have both your Hadoop data and your transactional data all in the same storage system. And we can support lots of different protocols. As Chris pointed out at the front end, we can support everything from iSCSI, Fiber Channel, and a variety of different protocols, including IB, to be able to access your data. And we optimize how the data is moved in a hierarchical storage system so that we move the data automatically from rotating media up to solid state drives to minimize the access time. And you can run all of your backups in the true background case so that you do not have to interfere with your ongoing Hadoop processes in order to take your backups. We've had customers that ran into this, and now with our Hadoop plugin, that solves that problem for them, that they can run all their background backups without interfering with the Hadoop process that's running in the foreground, because it's running a separate processor, a separate server, and it's running as a background low priority process. And that's all I had to cover for today. And contact us if you're interested in getting a copy of our proof of concept HDFS plugin, and we can point you at that code as it becomes available. So you can visit either Chris or myself after this.